Hi, my name is Dr. Amanda Hughes, and today I'm going to tell you about a project that I'm working on with Dr. Laurie Phillips at the University of Liverpool. The project is called Solar Skin, and it's about the additive manufacturing of fully customised solar cells into products. The aim that we're trying to achieve here is to get to a situation where we have solar cells everywhere in our everyday lives. Typically, at the moment, solar cells are seen as standalone products that you install in a large solar farm or in a home. And we're hoping to be able to integrate solar cells directly into products so that we can produce power at the point of need. There are a few good advantages to the kinds of solar cells that we're working on. We're working with thin film photovoltaics called perovskites. And some of the advantages of the perovskites are that the material themselves are tunable. So that means we can change the band gap and alter the type of light that's being absorbed by the cell so that we can optimize it to a particular environment. The composition of light can be really different whether you're in outer space, in the desert, inside of a room. So with these perovskites, we're able to tune that band gap to absorb the most of the available light in the given situation to maximize the electricity output. Another great advantage of being able to tune the band gap is that we can change the color of the cells so that we can match them to the aesthetics of a design. We're also looking at using additive manufacturing methods like 3D printing and inkjet printing to produce these solar cells. And one of the advantages of that is that we're able to produce the cell in a really specific shape, so they don't have to be the standard square that we're used to seeing. And this means that we'll be able to make interesting shapes and fill the space on products to produce as much electricity as possible. We're also looking at low temperature curing methods. And this is important because if we're going to be able to print these cells onto different surfaces, it would be useful to use lower temperatures when creating them. The higher the temperature, the more it limits us in terms of where we can put these solar cells. So to give you a little idea of how we go through this process, it's an iterative design process where we optimize the cell in terms of the materials we're using, the band gap of the perovskites, the thicknesses of the layer, and we can optimize the design of the cell for a specific application. And then we use various fabrication techniques like inkjet printing to actually fabricate prototypes. And the substrates that we're going to use for these are really varying. We're looking at two applications, both space applications and flexible electronic devices like tablets. And the substrates that we'd be printing onto, so the product we'd be printing onto, are really vastly different for those different applications. To give you an example, here we have something called PET, which is a plastic material that would be used in smartwatches, flexible phones, that sort of thing. And you can see here the substrate that we'd be printing on. It's pretty flexible, but it does kind of hold its shape somewhat. To contrast then, this is a kind of material called mylar, which is used in space applications. And you can see here that this sort of substrate is very flexible. So these are going to create different challenges when it comes to applying solar cells to them. It also creates a different challenge because they have different melting points, and this will limit the temperatures that we can use in the fabrication process. Once we've been able to fabricate on these different substrates, we will test the prototypes to figure out their electrical efficiency. We have a host of people working with us on this project. There's myself and Laurie at the University of Liverpool, but we're also working with industry partners Ecospheric, Solar Capture and Novacentric, who will be supporting us in developing these new and exciting products.